Hello, sir. Hello.
Yes.
Sir, my name is Shravana Vishwas. I will be the moderator for this session.
Good.
Sorry for the delay. We had some technical difficulty here.
No, it's still time.
So I will hand over this session to you now.
Okay. I will of course wait for 4 more minutes. But there's nothing. I mean, people can ask me questions in the meantime, if any of you have. Huh?
Sir?
Who is it?
Sir.
Dhruva.
Yes, sir. Sir, if I have a recursive function f of x1, x2, xn.
Yes.
And I have a permutation sigma.
Yes.
Then if I define a new function f sigma by f sigma of x1, x2, xn equal to f of x sigma 1 like that.
Yeah, they will be.
Is it also recursive?
Yes, because it is you get it by what is called substitution, recursive substitution. You see x1, x2, xn going to x sigma 1 is a recursive function because it is a projection.
Yes.
x1, x2, xn going to x sigma 2.
Yes.
Huh?
Yes, sir.
So you can permute coordinate, you can add coordinates. For example, suppose fx is a recursive function, and define gxy to be fx.
Okay.
Okay? Then is G recursive? Yes, because gxy is equal to f at pi 1 xy, pi 2 1 xy.
Yes, the first projection.
Yeah. So you can add coordinates, you can permute coordinates. All those things are allowed.
Yes, sir.
Okay. You can drop coordinates.
Yes.
So these are recursive.
Yes, sir. Thank you.
2 more minutes. There is a question in the chat box. No, this is not for me. Any more question or anything? I mean, regarding this course, I'm one of the program organizer also, so program coordinator also. So if you have to say anything, you are welcome. anything more we can do, it will help you out better, and this you can tell. Okay, so now it is nearly time, and so first of all, I want to thank Amit. Uh, yeah, I want to thank Amit for doing some job for me. Namely, he introduced things that I require for first order logic. There is a slight difference, but only a very slight difference between the way he has introduced, uh, not the way he has introduced, some of the things that is there in his presentation, which is absent in mine, and also to set up the, sort of link between you and me, I will little bit revise. Uh, I will say a few things more on first order logic. Not more, but let me share the screen. Yeah. So there is one difference between him and my presentation is that he includes parentheses in his language. I don't. And he displayed from my book uh, some of the axioms. So, for example, wait, let me make it full screen. Okay, let me minimize this. So, let me go to that place where you will understand what I mean. Yeah. You see here, when he said that if f is a n-ary function symbol, then and x1, x2, xn terms or variables, then we write fx1, x2, xn. I have not used parentheses. Okay. Here also, p is a n-ary predicate symbol, and I have not used parentheses. Okay. If you know arity of f, if you recognize that this guy is a n-ary predicate symbol, then you know that the n things that follows is the argument. And reason for it is particularly handy because less symbol you use, things about Gödel numbering becomes easier. And another thing that he was getting right here confused that, oh, I have not used any parentheses here. Okay. Now let me go back to yeah. So for example, this one. This is disjunction of phi with disjunction of psi or xi. And here disjunction of phi or psi with xi. When I don't use parentheses, I mean association to the right. So I would write according to my convention, phi or psi without parentheses. Or if you write A1 or A2 ... or AN, It is association to the right. That means I mean A1 or, and now parenthesis begins that A1 disjunction rest of it. So the rest of it is put in bracket. But then A2, the what is in the bracket is disjunction of A2 with the rest. Then I put the bracket. Now, if you keep on doing that, too many parentheses are used. So if you use the convention of association to the right, you don't have to use parentheses. So when parenthesis is not used, then it means convention association to the right. Now let me come back. Sorry, let me go back to axiom. That one. Now here what I mean is that x1 equal to y1 implies the rest. So what Amit will do is that Amit will put a parenthesis here. I have not put a parenthesis here. Okay. Then x2 implies y2, and then Amit will put a parenthesis. I have not put a parenthesis because it does mean that it is association to the right. And it says if x1 equal to y1 is 2, that implies x2 equal to y2 this 2. If you read whole thing, it will just mean that if all these are true, then f of x1, x2 equal to f of y1, y2, y1. These things are done with the Gödel numbering in mind. Less symbol you use, less complicated the Gödel number is. So this please keep in mind that I am not using parentheses. However, formally I am not using parentheses. So, so if I go back to fraction of number theory that I was describing, you see I am using parentheses. Okay. So when I do it, when I'm doing actual work, I use parentheses to avoid confusion. But formally, I don't have to use parentheses. Okay. So parentheses are used in the usual way, just for unique readability, so that at times it becomes confusing. You don't get confused. Logically, from logic point of view, parenthesis has no role. It has no logical meaning. It is only meant for avoid ambiguity. Okay, and if you bring a convention, keep a convention clear that what is your convention, then you can write down everything without parentheses. Okay, provided you know the convention. Another thing that he did, and I liked it, which is
Sir,
yes.
with this convention of association to the right, how do we
Yes.
capture this formula? Like A or B or C or D? Like I have 4 and I club.
No. So first of all, you see, depends how I'm writing. If I write without parentheses, A or B or C or D,
Yes.
then it will mean A or parenthesis begins, B or parenthesis begins, then you write C or D, and then put 3 parentheses, other parentheses, right parentheses. That is the convention.
But sir, then
Okay?
aren't we missing on the following formula, like A or B or C or D? Like first two brackets.
Not logically, yes. Formally, yes. That expression, I'm not saying that if you want to say that A or B parenthesis or C or D.
Yes.
Okay. Now you see, actually we don't write A or B. We write all AB.
Yes.
Okay.
Yes.
So what I will do is that, and he was doing it in his example, that no parenthesis. First of all, it is the conjunction of A or B and C or D. Sorry, disjunction of A or B and C or D. Okay, so I will put for this disjunction, I will begin with the disjunction symbol.
Yes.
But disjunction is a binary thing. So what are my two things? The first one is A or B.
Yes.
Then I will put again a disjunction
Or
and
C-
put
C-
B, A, B.
Yes.
Okay?
Mhm.
And the next one will be disjunction
Mhm.
CD.
Yes, sir.
Okay?
Yes, sir.
That is how formally it will be written without parentheses.
Yes, sir. Got it.
But
Thank
but I will drive all of you crazy if I start writing like this.
you.
Huh? So it is only for the convenience of unique readability, those things are used. So it is not that we don't use it, huh? But so far as the formal logic is concerned, parenthesis does not exist. We have very strong convention,
Yes.
huh? Very fixed convention by which we avoid parenthesis.
Yes.
Reason of it will become again clear that when I will do total numbering, huh? Then the sequence has become much smaller, huh? If you don't use parenthesis. Okay? It has become much smaller and it helps. So that you will see. Okay? Another thing that he was doing, that this one. So suppose f is a binary function symbol plus, and in conventionally what do we write? X1 plus x2. But today you saw that formally it is plus x1 x2. When you wrote x square minus 2x plus 1, that is what you do in mathematics. That is the language you are used to. But how did he do that? Okay, he didn't write x square. For x square, he wrote dot xx. He put parenthesis after dot. I will not put parenthesis after dot. Then what did he do for 2x? He wrote plus xx. Put xx in the comma, in the parenthesis. Okay, and so on. So if you go and see his note, he's doing that, but he's also using parenthesis, but with convention, like I have described you, I can write down the same thing without parenthesis. Okay, and you may notice that I have also not used commas anywhere. Okay, so if I know that this is a n-ary predicate, n-ary function symbol, then I know that what follows, the next n item will be the argument of n. Okay, this may be a term, ft1, t2, tn. It could be that, but I know that this f operates on the next one. I don't have need to put next n1. I don't have the need to put commas at all. But if I am so strict, if I remain so strictly formal, you will all go crazy. I will also go crazy. So we will go back to our usual mathematical convention, but you know that there is a translation in a formal language. Okay, this is one thing. And for example, very soon I will come. You see, I have used parentheses, this, that. Now, it is very easy for you to read. For example, let us see this, that for all x, for all y, x less than y, or x equal to y, or y less than x. Now, if I try to write this in a my way, it will drive all of us crazy. But in our mind, it should be clear that formally what is the corresponding relation. You see here, I have not written plus x, xy. Okay. Here, I have not written x plus xy. But formally, it is x. That means I am applying successor, a unary function symbol. And what I am applying? To plus xy. Okay, so all of these have a formal counterpart. And so while I will be doing Gödel numbering, I will use those formal counterparts to associate numbers and not these. Okay, this is very, very important to notice that in logic, the formation of the sentences, formation of the terms are very, very precisely defined without any ambiguity. This is what is difference between a natural language and a formal language. But the formal language, will drive reading through just formal language will drive human being crazy, but not the computer crazy. Okay, because they have been given proper instruction. So this is something that should be clear. Okay, so let me go back. Okay, now I'm not, so you know what are the first order languages. And he used almost the same. He used conjunction, I used disjunction in the part of my language. And for him, once he has done conjunction, taken conjunction and negation, disjunction is a defined symbol. Okay? And he used existential quantifier, and universal quantifier is a defined symbol. But it is so defined that it captures the meaning, the intended meaning. Similarly, he has not defined implied, right arrow. A implies B. That is the abbreviation for negation A or B. Okay? But all these things are, defined symbol. On the other hand, we will use them freely. That wherever I say A implies B, I mean negation A or B. Wherever I say for all x, P, actually it is negation, there exists x, negation P. Okay? But we will go back and translate everything into the language that mathematicians use. Okay? So that is only for convenience, for less confusion. In formal language, reading will be crazy even by a very seasoned logician. They will not do that. Okay? Formality is needed because now things have to be unambiguous and very well defined. Okay. Now he has defined terms, he has defined formulas, and he has defined first order theory. Incidentally, for me, again, the convention that I follow, for each language, it is true that you have to only indicate non-logical symbols. Okay? For example, if you are doing, let's say, group theory, then it has only two non-logical symbols, one binary symbol for binary function symbol, binary group operation, and another for a constant symbol for the group identity. So no, so most of the people distinguish between. In fact, quite often they say that a language or signature of a language consists of what are the special symbols for that particular language. However, when you start making terms and formulas and such, you use other logical symbols which are present in, which are common to all theories, like variables, then logical connectives. So in my case, they are negation or logical quantifier. In my case, and so was in Amit's case, it is there exists, and there is a equality symbol. Okay, and then followed by your set of constant symbols. For each n, a set of for each n greater than equal to 1, a set of n-ary function symbol, and for each n greater than equal to 1, a set of n-ary relation symbol. And mind it, neither Amit nor I am saying that these sets are non-empty. All these sets. For example, when you do set theory, the non-logical symbol, there is only one. A binary relation symbol belongs to epsilon, what is a common notation. So there is no constant symbol. So set of constant symbol is empty. There is no function symbol of any arity. All those are empty. Only the set of binary function symbol is non-empty, and it consists of just one symbol belongs. Okay, so you may have, in fact, most of the interesting theories, whether you are doing like group theory that I just now told you, has only one binary function symbol and one constant symbol, nothing else. If you are doing rings, maybe rings with identity, then you have two constant symbols, 0 and 1, which we denote by 0 and 1. Two binary function symbols and nothing else. If you want to do ordered field, you may have less than also. So some of these may be there, may not be there. In fact, there may be no non-logical. Suppose I want to say that, oh, I want to study theory of infinite sets only. Okay? Then you don't have to worry for any symbol. You just write down infinitely many axioms. X0 is not equal to X1. Then X0 is not equal to X1, and X1 is not equal to X2, and X0. I mean, for each n you write down that in many distinct elements are there. Okay, a formula. And models of them will be all infinite. So it could be, it's quite general. And the way I view logic, first order logic, is you see somebody on the street quite often asks, what the hell is a, or suppose a physicist asks you, what the hell mathematicians do? And then if you are doing group theory, then you say, sir, I do group theory. So what is a group? Oh, a group is a non-empty set with this, and so on. Somebody will say, oh, I do commutative algebra. Somebody will say, oh, I do linear algebra, vector spaces over C only, and so on. The way I view the first order logic should be viewed is unified language. That they study structures with given which has certain fixed constant symbol, certain fixed function symbols, certain fixed relation symbol, and which satisfies certain actions. Okay, I have unified. I have described all mathematical theory in a unified way. And it is my slogan that mathematical logic or the first order logic is a perfect way of is a way of doing mathematics in perfect generality. We are studying theory of theory. Another name for it is meta-mathematics, mathematics of mathematics. We are studying all these theories mathematically. So that is how I view, and we want to put them into one single setting. Okay, so let us, since there are a few conventions that I will be following, and Amit didn't have reason to tell, so I am telling you. So first of all, I have fixed, as Amit said, we have to have countably infinitely many variables, so that whenever you need a variable, new variable, it is available to you. Whatever expressions and such terms, formulas, whatever is needed, they are all finite. So any particular one of them will use only finitely many variables, but you can't put an upper bound. How many variables? So if you take a sequence of variables, you will be able to express everything, all expressions. Okay? And mind it, I am saying I fix an element. Okay? So it is in a definite order. These are called variables, and this I call the alphabetical order of variables, which I have not written. But in practice, X, Y, Z, U, V, W, they will be used at, at random, without any hesitation as variables, meaning that they are one of these variables. Okay? Now, here T is a term, and when I write this, it will mean that it is a term in which no variable other than x0, xn minus 1 occur. I am not saying that each one of them occur, but nothing other than these will occur. No variable other than these will occur. Then I will use this notation. And here I have made it clear, it may so happen that some or even all of these may not occur. And what is a term T? As Amit has described, you will start with variables. Variables are terms, constant symbols are terms, and go on operating your function symbol. So all that you get are called terms. So there may be terms where you have only operated function symbols on constants. Okay? Therefore, there are no variables. So these are also called variable-free terms. Similarly, when I have formula, so he defined atomic formula. Okay? And then, so atomic formulas are like T1 equal to T2, where T1, T2 are terms, or sorry, one thing that I wanted to say earlier. So all logical and non-logical symbols constitute my language. My definition of language is that. And I don't like this terminology. I would have liked to call them alphabets. Precisely using those things, you form an expression, you form a term, you form a this. So they are called alphabets. I would like to call them, but it has become convention to call this a first order language. To me, a language consists of everything. It's not just its alphabets, not just A to Z. Hmm. So fancy these things which have been done as alphabets of what I am going to, the language that I am going to develop. That is one thing. And so I will call them alphabet. There was a question to Bibi Rao that why is for all I, xi belongs to, or AI belongs to X. No, I think xi belongs to AI. Is not a formula of set theory. You see, I is not in the language of set. Okay? You are not allowed to use any other symbol than what is in your alphabet. Just imagine you are writing something, and here I use letters from Devanagari and Tamil and this together. How will it sound? It's not allowed. You are only allowed to use letters from your alphabet. Okay? Only they are the formula of that theory. Nothing else is a formula. This is a point that should be noted. Because in real life, you say, oh, for every integer, n, p, n holds. Okay? What logicians will say is that they will have a sequence of statements P1, P2, P3, dot, dot, dot. And then there will be a meta statement saying that each Pn holds. That is how they will say. What BBR wanted to say is that for each I, when he had a formula that A1 belongs to, X1 belongs to A1 and X2 belongs to A2. Okay? He had just used the disjunction of two sentences of the set theory. Or X1 belongs to A1 and X2 belongs to A2, dot, 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 and Xn belongs to A. This is valid. But you can't say for all n, because this n is not a part of your variable, of your alphabet. So this is one distinction that one must keep in mind. Okay, so you know what are atomic formulas, and then you iterate or negation, and there exist. As I told you, there is a difference between me and Amit. I am using or, Amit used and. That means disjunction, negation, or in the way that he has described, and you get all formulas. And if you don't use quantifiers, then he said they are quantifier-free formula. I also call them closed formula. Open formula. Okay, I intervened and told him that I also call them open formula. Because you are going to just, very next lecture is going to be mine. And if there is no free occurrence, this is zero. See, this may be a closed formula because none of them may occur. Okay, but if I only write phi and mention that it is a closed formula, that means there is no free occurrence of any variable. And that I call a closed formula or extending. Okay. Now there is a question of substitutability. Huh? Yeah. So I'm going to define a new formula like this. Okay. Here phi is a formula. V1, V2, Vn are distinct variables, and T1, T2, Tn are terms. Okay. And then I'm going to define a creature like this. And if from the context V1, V2, Vn are understood, I subtext that or brevity. Otherwise, things will be confused. But let us read this. This is a very crucial point, which Amit has not covered. We say that a term is substitutable for a variable v in a formula phi. You cannot arbitrarily substitute any term for a variable in a formula phi, because essentially the meaning should not change. Now let us read it to understand it a bit better. If for each w occurring in T, so suppose w is a variable that is occurring in T, there is no subformula phi. So now here is a concept subformula. You see, definition of formula is inductive. You have started with atomic formula, then you form disjunction or conjunction or disjunction or negation or existential quantifier. So whatever formula you use to do disjunction, they become the subformula. So you can see that each formula is built up of various things. So whatever sub part of the formula is that went into building it are called subformula. Okay. So a variable w occurring in T, or take any variable w occurring in T, there is no subformula phi of the form there exists w psi, such that in psi v has a free occurrence. Because what happens is that here v is free, but T has w. So suppose I write, my psi where x equal to y square, and my T is x plus x. Okay. Or let's say I have this, there exists x equal to y square. Okay. And my T contains w. There exists x. Yes. And my T is x. Suppose. Then if I substitute for y, T, then I'm saying there exists x equal to x square. The total thing changes. Such things are not allowed. Okay? So you can substitute a term for a variable in a formula if there is no subformula of this form where v has a free occurrence and w occurs in T. And just now I gave you the example that suppose I have T is x, variable x, and my formula is there exists x equal to y square, and v is y. Then I am not allowed to substitute x for y, because it now becomes there exists x equal to x. Okay? And that will never be true. On the other hand, so these kind of things have to be, under these circumstances, they have to be avoided. And now here comes this, that suppose they are, each of these T1, T2, Tn are substitutable for distinct variables, V1, V2, Vn, I should have written respectively, in a formula phi, then this will denote, what you do is that simultaneously, each occurrences of free occurrences of Vi, you replace by Ti, each occurrence of V1, you replace by free occurrence of V1, you replace by T1. Wherever there are free occurrence of V2, replace by T2, and so on. Simultaneously, not one by one. Because it may so happen that, you have first substituted T1 for V1, but in that T1, V2 occurs. Okay? No. Simultaneously, physically, simultaneously, plug out V1, V2, Vn, and wherever there are V1, you plug in T1. Wherever there was V2, you plug in T2. Wherever there was Vn, plug in T. That is what it will denote. And one axiom he fumbled a bit, that what does it mean? And let me go back to that substitution axiom. Yeah. So this one meant that E is a term which is substitutable for x in phi, then such thing is called an axiom, logical. Okay? This is what was this axiom. Since Amit had little bit of difficulty because he is not still completely in tune with my language, I've gone back and okay, so this is something that should be remembered. Okay, let me go. Now, I was harping on saying that Gödel's theorem, weakness or strongness of Gödel's incompleteness theorem. So roughly speaking, Gödel's incompleteness theorem says that if T is a theory, consistent theory, which is a stronger than, and this is stronger I will explain you later, than a fragment of number theory, then it will be incomplete. Okay? Any such theory will be incomplete. And by incompleteness, I mean there will be a sentence which will be not decidable in the theory, meaning that neither that is a theorem of T, nor its negation is a theorem. So what is that small, and obviously to make the theorem stronger, you would like to put this condition as weak as possible. So what is that weak fraction of number theory that goes into the hypothesis of Gödel's theorem, and that is what I am describing. It is not the full description of number theory. The conventional axioms for number theory, piano. So it has a constant symbol, 0. It has a unary function symbol, x, and I am naming each one of them. This I am calling successor function, but this is a symbol only. There are two binary function symbol, addition and multiplication, and a binary relation symbol. You can compare integers, you can add numbers, you have the function n going to n plus 1, and a constant symbol 0. And mine is natural numbers, so only things begin from 0. And what are the axioms? non-logical axioms, I mean. Moment you have defined, given the language, okay, let me go back to that part. Logical axiom. Okay, you see, first thing is that, is it one axiom or many axioms? It is a axiom schema. For each formula phi, this is an axiom. Okay, even though my list has only A, B, C, D, means 4, or if you count this as different, only 5 things written. Okay, but no, this is countably infinite. This may be infinitely many formulas. It depends on how many non-logical symbols you have. So for each formula, this is a formula. This is an axiom. I have written x a variable, but then I will need a theorem which will say that if this is a theorem, then replace x by any variable that equal to this is also a theorem. So in order to avoid that, I have put here, by here a I mean any variable. That means this is also x0 equal to x0, x1 equal to x1, x2 equal to x2, and then here also, this is not one axiom. This is a infinitely many axioms. For each variable phi, for each formula phi, for each x variable x, for each term t, I have a formula. Okay, and I consider only those where t is substitutable for x. Okay, similarly here, for each n-ary function symbol, I have this, and mind it, I'm using y1. I'm using yn. These were not my variables. Variables are x0, x1, x2, dot, dot, dot. So here also these are not x1, x2, xn of my alphabet. These are general variables. Okay? So this happens, this happens. So these are the axioms. Okay, so let me go back. So what I want to say is that once you have given the language, you know what are your logical axioms. Okay? Then depending on your theory, you write down your axioms. For example, if you are doing group theory, you don't say all the logical axioms. You only say what are the axioms of group theory. So these are my non-logical symbols of the fraction of number theory that I am using. It is just saying that successor of any x, mind it, x varies over model, standard model for me is natural number. So successor x is never less than 0. It is not equal to 0. Okay? Here it is saying that successor is a one-to-one function. And usual, x plus 0 is x. X dot 0 is x. There is no negative number. Okay? This is how induction goes, how plus and x are related. So x plus successor y is successor of x plus y. X dot successor y. So think of this as y plus 1. So what it will be? X dot y plus x. Okay. Then integers are comparable, what madam called trichotomy. Then x less than y plus 1 is same as saying x is less than y or x equal to y. Okay, these are my axioms. So this is a theory that will play a crucial role in Gödel's incompleteness. And in this theory, I have a formal counterpart of natural. So mind it, 0, and I am applying x to it n times. Okay, so this is a term. This is a syntactical object. Okay, and instead of writing in such a complicated way, I really had a tough time. I had to look for the LaTeX command and so on and so forth to write this. So instead of writing this will denote this particular term. And if n is 0, you have not used x at all. So K0 stands for the term. Okay. Now, if you think of the standard model, and there if you take the interpretation, then interpretation of Kn will be the integer n. The interpretation of K0 will be integer g. Okay? So this is the syntactical counterpart of natural number. Okay, this is what I have done. Okay, so now here it will test your understanding, how much you have understood so far. Now, open formulas or quantify free formulas, how do you get? It's the smallest set of formulas of n that contains all atomic formulas and which is closed under negation and disjunction. Okay? So, this is what open formulas are of n are. Since this is the case, if you take any formula with these possible free variables, then you look at set of all n tuples of natural numbers such that, oh, by the way, omega, let me go back again. Omega is a structure, what Amit defined there. So I have to interpret all these logical symbols. I define it by usual meaning. The constant symbol 0 is interpreted as the natural number 0. The successor symbol x is interpreted as the function which takes n to n plus 1. Binary function symbol plus is interpreted as the function addition on natural number, usual addition. Similarly, multiplication, and similarly, less than, because you have a less than on natural numbers. So you know the set of natural numbers, and on that set, these are the interpretation. And then you can see that not only that it is a structure for this language, it is a model of this theory. Model of a theory means that so far here is a defined truth that all these statements are true in your structure. Okay? So set of natural number is a model of n. And these are all very obvious properties of natural numbers. And that is why it is a very small fragment of number theory that Gödel is just. Okay. So now, well, take any open formula in possibly these free variables or free variables among these. And then, anyway, these are constant symbols. Constant symbols are always substitutable because there is no variable occurring in them. Or variable free terms are always substitutable for every variable. Because the restriction is that if some variable occurs in a term, then something else should also be satisfied before substituting. So this replacing x0 xn minus 1 by km0 km minus 1 is valid. Now it becomes a sentence because there is no free variable here. And I am looking at all those n tuples which satisfies this. And I am calling it recursive. Okay? I'm calling it recursive. So, no, I'm not calling it recursive. I'm asserting that these are recursive. Okay? I have given you this. Now, suppose phi is an atomic formula. Then the list of recursive sets that I have given you, for each atomic formula, if you write down that when it is true, maybe 2 plus 3 equal to 5. Okay? Your 5, your phi x0, x1, x2 may be x0 plus x1 equal to x2. Okay? Your m0 may be 10, your m1 may be 12, your m2 may be 22. In that case, it is true. So essentially what it is saying is that go through all atomic formulas and then check that this set will describe you a recursive set. You will find it in the list of my recursive predicates that I have given you, or you can very easily check. You just have to write down what are the terms, what are the terms, and then you substitute it. Terms are made up of what? Successor function, n going to n plus 1, which is a recursive function, or addition, or multiplication. All these are recursive functions. And then you are only composing them. Okay? Because, terms means you apply f to f to f to g to g to h. That means you are repeatedly applying. So it's like you are composing various these initial functions operating on those. So it should not be very hard for you to imagine that if phi is atomic, then this set will be atomic. And now you only have to use the fact that the set of recursive predicate is closed under negation. Because if this guy is if this guy is recursive for phi, and I replace negation phi, then we are looking at the complement. And complement of a recursive set is recursive. Okay? So the set of all phi for which this statement holds is closed under negation. And if this statement is that this is recursive holds for two formulas, phi and psi, then if you put phi or psi, x1, x2, xn minus 1, km0, km minus 1, then you are only taking union of two recursive functions, recursive set. That will be recursive. Okay? And therefore the result will follow. Okay? So I hope you are convinced. So this is the hint given. If you are not convinced, you please sit down and convince yourself. You see the connection between recursive function and natural numbers, the theory. the first order. Okay, so now the proof he has defined. So I have given you the set of my axioms and the rules of inference. Okay. By the way, Amit had only one rule of inference, mod exponents, but he had many, 4, I think, logical actions for the propositional logic. Okay, and suppose you forget all these things which will require first order language. Suppose I have a propositional logic only, and then this phi is a formula for that language. So if I assume this to be as my logical axiom only, and these to be my rules of inference, then you define formal proof exactly the same way as Amit did. Then it will be true that a formula phi is a logical consequence of a set of formulas T if and only if phi has a formal proof with T as the set of X. Okay? And I think he didn't give the proof of propositional completeness axiom even for propositional logic. Is that right, Amit?
I did give the proof for completeness theorem.
I gave you reference of my book, Baba. Huh? Post-tautology theorem. Okay, there is another proof in my book because I use different system, deductive system. Okay, now there are lots of deductive systems. The reason that Amit's thing is more popular nowadays, particularly among computer scientists, is that because it has only one rule of inference, mod exponents, it can be implemented on computer more easily. And there is what is called sequent analysis. Okay. So nowadays, particularly computer scientists prefer what Amit has done. Okay. Okay. So where was I? Why did I come here? Let me go back to previous thing. Okay. So these you have already seen, and I'm not going to show you again. And proof is defined exactly the same way as in propositional logic. It is a finite sequence of formulas, so that if you are here anywhere, then either that guy is an axiom, logical or non-logical, or this can be inferred from the previous one by one of the rule of inference. And this sequence, I will call it a proof of what occurs in the law. Okay? And theorems are precisely those which has a proof in the theory. Okay? So this is my notation. That is also the notation of Amit, that this is now syntactical proof. Okay? If I put double, it means that in all models of T, phi is true. Okay? And this one is that there is a finitary proof. This is called also Hilbertian style thing, deductive system, because when I opened my lecture, I did tell you that, you know, at the end of 19th century or the beginning of 20th century, by the way, I'm not able to see time, so I should be forewarned. Oh, So 2, 3, 4. So please, the chairman, sir, please give me a warning about 10 minutes before my time is up.
Sure, sir.
Okay. So, okay. This is the thing. And now you see, uh, uh, one of the things that is funny here is that, or very striking here is that, never mathematicians cared to know that proof has to be defined. Okay? You ask that guy, hey, proof. What is the definition of a proof? And they will shoo you away. Okay? That is because they are doing semantic. Whole mathematics and actual professional mathematicians who do, they verify a statement in all models, and the logical axioms are understood, because there also they are doing. I mean, if somebody says, oh, let G be a group, and then you think that you are doing very concrete thing, you are only fooling yourself. Which group? There are as many groups, as many sets are. Okay, of course you are talking very abstractly. Okay, and then okay, there is a notion of truth, which follows this whatever logic they are doing, and this is being formalized. And Hilbert's program was that you have to write down a set of logical axioms and a set of rules of inference, so that anything is a theorem semantically if and only if it has a finite proof. Okay, a very profound question he asked. He said, oh, you should be able to write it down. And having defined this notion of a proof, then I think he was mainly interested in number theory, because till then this general notion of theory and logic had not come. And then he said that you will be able to find a set of axioms for number theory, such that given any statement about this, I doubt that, or maybe he knew, because he himself developed this Hilbert Ackerman book and so on, that at least for the first order statements, every first order statement, either that will have a proof or its negation will have. And a lot had to be done by Gödel to precisely state Hilbert's program mathematically. A lot had to be done. Because he had to read the mind of Hilbert. Hilbert, as you know, was the frontline mathematician of that time. And he set up this program, and quietly in a corner of Vienna, this young boy alone worked on that. Incidentally, I have gone to Vienna just to pay my homage to Gödel. So I was in Gödel Research Center, and they respect, all Viennese respect, know the name of Gödel, very respectful to him. And on the very first day, when I was approaching from my hotel to Gödel Research Center, as soon as I crossed the road, little away from the institute, I saw a plaque on a building. And then I read, and it said, oh, here stayed Gödel. I took a picture, madam was with me. We are seeing Gödel's house. So I went and told my host, Sai Friedman, Sai, I saw today Gödel's house. He said, no, Gödel did not stay in one house. Over a period of time, he stayed in various houses. So on his birth centenary, they found out all those houses, and on all those houses, they have put a plaque that here stayed Gödel. That is the esteem in which they keep. Of course, he has a statue inside Vienna University, along with many other Austrian mathematicians, but that is only expected. But I mean, so much he is regarded that all the houses where he stayed, there is a plaque saying that here he stayed. Okay. So this is also the definition of Amit. A first order theory is consistent if not all formulas is. Otherwise, it is called inconsistent. So remember this. T is called consistent. Complete if it is consistent, and for every closed formula. Okay? Phi or negation phi is it. Okay? For every closed formula. So I have come to a stage where there is one more theorem, one more thing that I should have said. Closure of a. No, I have not said it. I have said it later. Just a second. Okay. Let me go back and define in words by my mouth. Yeah. Look at this formula. So suppose you have a formula like this in which no variable other than x0, x1, xn minus 1 holds is free, and xn minus 1 has at least one free occurrence. Okay? Then you consider the formula for all x0, for all x1, dot, 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 for all xn minus 1, pi x0, xn minus 1. Now, all the variables have become bound. But I have been very specific. Here I have used the alphabetical order, and I'm saying that I stop at the place where the last free variable. Okay? And then I put universal quantifiers in this order for all x0, for all x1, x1, dot, 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 for all xn, pi x0, xn minus 1. This is a well-defined formula, and it is called the closure of the formula phi. Okay? This I have not mentioned here, but this I will need in the arithmetization. In Gödel's theorem, I mean, not arithmetization. Okay. So, any question? I'm giving you time for question now because now I will enter Gödel number. Any question? Anything that you need to be explained?
Participants can unmute and ask the question.
It seems no. And whenever there is a silence, I assume one of the two extremes. Everybody has followed everything, nobody has followed anything. In either way, I can continue. Okay. Now comes the thing. You see, these are just symbols, your alphabets. Okay? What happens if I had used here V0, V1, V2, dot, dot, dot? Nothing. What here if I had used twiddle, which many people do for negation? Or what happens here if I have used the word or? Nothing. I mean, I'm at my liberty. And instead of this, I would have put E. And so long as I know what they mean and so on, it does not matter what symbols you use. Okay? So these are formally only symbols. So what we use for them does not matter. And what Gödel does is that in a very systematic way, instead of using these, he uses numbers for them. Okay? And then once he assigns numbers to them, then what happens is each of these syntactical objects, whether it is a term, whether it is a formula, where it is a proof, is a sequence of, is a finite sequence of these. And then he quotes them. The coding is done in such a way that decoding gives, decoding can be done recursively, and recursively you can decide what those numbers represent. Okay, so that is the project he took, and this is what is commonly done even these days, that your input may come from anywhere, and you have to worry how to feed them into the computer. And therefore, you turn them into numbers, your input. In fact, those who are from computer science background and know Turing machines, you know that each Turing machine can be represented by, I mean, they know that each Turing machine itself can be represented by a number, natural number. Okay, so this idea of Gödel continues, and that is why I call Gödel a father of computer science also. Because not only he defined the notion of algorithm, he was the first to define. He also defined that, okay, your problem may come, your decision problem or your computational problem, whatever you want to come, may come from any damn branch of mathematics or this. And if you want to compute them, you have to digitally, through computer, through mechanically, then you have to translate it into numbers, and that continues. And this is the first time it is done. Now, here is a serious restriction in Gödel's theorem.
Sir, sorry to interrupt you.
Yeah, sure.
You have 10 more minutes.
Okay, good.
Conclude.
Yeah. So, now we know our logical symbols. Non-logical symbols as such can be anything, but there is a restriction because I want to do everything in a mechanical fashion, that in Gödel's theorem, each theory has only finitely many non-logical. With some difficulty, with some effort, you may say that, okay, there can be recursively enumerated. That means not more than countably. And not only that, you can enumerate it in such a way that given the number, mechanically you can decide which non-logical symbol that number represents. But we will not go into this, Gödel himself confined to finitely many non-logical symbols. And if you run your eyes through the theories that you are familiar with, they only have, concrete theories like number theory, ring theory of groups, theory of rings, theory of ordered fields, and so on. They all have finitely many non-logical symbols. So Gödel makes this assumption. So Gödel represents them by numbers in a systematic manner such that one immediately sees if a number represents a symbol of L or not. That also it decides. And if so, which symbol it represents. Huh? So this was fantastic, and you will see the effect. Using this trick, one represents each input of a decision problem from any branch of mathematics into a number. Thus, every decision problem is turned into a decision problem for numbers, as I was telling you. By here, I mean every decision problem, I mean decision problem from any branch of mathematics. It may be graphs, it may be whatever. Something about input of a linear programming problem or transportation problem, whatever algorithmic thing you are doing. A number through its binary representation can be, this I have already done. And this also I have said, I will not repeat. So I come here. From now onwards, we fix a theory T with finitely many non-logical symbols and denote its language by L. So here is a restriction, finitely many non-logical. Now, so I assign to each alphabet what is called the symbol number of that. So this dot is just, function, symbol number, and here there will be some alphabet. So symbol number of ith variable is 2i. In other words, each xi represents xi by 2i. So you have represented this countably infinite many variables by even integers. Only odd integers are at your disposal. So you do symbol number of negation by 1, symbol name or by 3, there exists by 5, and symbol number of equality by 7. We fix once for all an enumeration of the finitely many non-logical symbols. So as I said it, there are only finitely many. And I want to decode back also. So once you fix the enumeration, if they were infinite, then this enumeration may not be recursive. But for finite case, it will not cause a problem. So you can enumerate in any way that you wish. And then ith non-logical symbol, because up to 7 you have exhausted. So all even numbers are exhausted, and odd numbers up to 7 are exhausted. So you put them to be 7 plus 2. Okay. Now, each syntactical object is a finite sequence of symbols in L. It is represented by a finite sequence of numbers now, which in turn can be coded by a single number. We call that number the Gödel number of the object. So now we proceed. Now, just I will give you a stop pretty soon. In fact, probably after this, from this slide. You see, given a number n, consider the decision problem. Is n a symbol number of a variable? Okay. So this is what is the question. Is n, so if you consider variable as the unary predicate consisting of symbol numbers of all variables, then this is saying that n is the symbol number of a variable. And when is the n a symbol number of variable? If and only if n is even. If and only if 2 equal to n. In other words, I can, excuse me, I can, given n, I can determine, I can mechanically decide whether n represents represents a symbol number of a variable, and if it does, then which variable? Okay, because I can also find the quotient. That if it is an odd number, then if it is an even number, then n equal to 2i, how I will express? I has to be less than n. So there exists I less than n, 2i equal to n. That is a recursive predicate, and this I can extract out, that 2i equal to n. That I can extract out, and I will call it that ith variable it will represent. Now, constant symbols, it's only a finite set. That is a recursive set. N is the symbol number of a function symbol. That is also a finite set. So it is a recursive predicate. Then again, there are only finitely many recursive predicate symbols. So that these are all recursive sets. Okay, and you know precisely that given n, is it even? Is it of the form 2i? If yes, then it represents xi. Is it 1? Then it represents negation. Is it 2? Is it 3? It represents or. Is it 5? And so on. So you can decipher this. And finally, S and N is the predicate that N is the symbol number of an alphabet in L, and that is also recursive because it is a disjunction of finitely many recursive predicates. Okay, let me stop here, and if chairman allows, yeah, at least when does my lecture end? Oh, I still have 3 minutes. Then I'm doing fine. So 3 minutes is mine. There, chairman cannot have any say. But after 3 minutes, he will say when to stop. So questions. And first, before that, one Mr. Ranjan Mukhopadhyay has to show me his face, as he promised me yesterday. No camera.
The host has disabled. The host has disabled it.
Oh, camera is disabled.
Sir, I have enabled it again, so you can start camera now.
Okay, buro egacho.
Yes.
Okay, nice seeing you. Okay,
Yes.
okay.
Fine. It was very nice to hear you speak so well. I was really waiting for this topic and your lecture. Okay. So but now I have a question.
No. Before that, let me ask you, will you still ask people forewarn that they stay away from him? This guy is crazy about mathematics.
I will forewarn those people who are afraid of mathematics. But those who love mathematics, just as I do, I will not tell them this thing. I will rather tell them that they meet you and be companion to you. That is what I want.
Because you are forewarning people not to keep away. This guy is crazy about mathematics. Okay. So now I have seen you. It is your choice whether you will keep camera on or not.
Okay.
But yes, your question.
Yes. So my question is, I have understood it so far very clearly, but I just wanted to know how to distinguish between two formulas. like a formula will be starting with this 1, 2, 3, 5, 7, etc. And then, okay, I will have another formula, especially when I have a proof. The proof is also Gödel numbered. So the proof is a sequence of formulas. So how do I then space out the different formulas in the sequence?
No, that is the coding will tell you.
Acha, okay. I will wait for that then. Okay.
The coding will decipher back all the coordinates.
Okay.
And then each one of will tell you that which formula, each coordinate will tell you which formula is there.
I see. Okay.
Okay.
Thank you.
Yes. Any question? Nikita? You have never asked me a question in mathematics. Is she there or not? Okay. So it seems again, I go with either of these conclusions.
Thank you, sir, for this interactive session.
Okay.
So,
Yeah. I will leave the meeting last. I mean, when because I will stay whenever. I think I should stay for students to ask me questions.
sure, sir.
So if you, it seems there is no question. So if you think so, you can close the meeting. But I am not going to close the meeting.
So participants can ask the question now, and if they don't have any question, we can. We can take a break and start.
Oh, acha. Now Amit is lecturing. There is one more lecture.
4. So up to 4, we can take the questions maybe.
Okay, then I am sitting here. I will just get water for me.
Sure, sir.
Okay, we can chat. I will. Yeah, you can chat also.
Excuse me, sir.
Yes.
So I just wanted some clarification regarding this last part, the definition of symbol numbers. So like just with an example. So suppose I have x1 or x2, the like evaluation of the symbol, like the symbol number for in this case.
No, x1 or x2 is not a symbol.
Okay. What was the thing that you said, sir, that will define a sequence for...
No, that I have still not come.
Okay, sir.
I have only assigned numbers to variables.
And logical connectives.
Logical connectives, quantifier, equality symbol, and non-logical.
Okay, sir.
Okay. It will be good if you somehow little bit because now lot of predicates will be written, and I will run my finger and show you why they are recursive, and some amount of grip over recursive functions and recursive predicate is required at that place. It's like your proficiency in handling addition, subtraction, multiplication, division, and so on. And then compute various arithmetical. Okay.
Sir,
Who is it?
Sir,
Abhiraj
Abhiraj.
Singh. Yeah.
Yes, sir, can you tell like about your present field of work? Something about you?
At the moment, I am only teaching.
Right, sir.
Okay, but I'm more. For example, very recently, me and my wife have written a book in model theory.
Okay,
And
okay.
then during pandemic, I have written a book in set theory. Okay. But
Yes,
my
sir.
original research was in descriptive set theory
Okay,
on
okay.
selection theorems.
Yes,
Okay.
sir. Yes, sir.
But currently, I'm just teaching and teaching and teaching and writing and writing and writing.
Yes, sir.
I think that also somebody has to do. Because, well, it gives me a great pleasure to know that a lot of people are learning, are reading my book internationally. Oral sets is very famous. Logic is also many people are learning. So I think I am making a contribution to the society. Yes.
That's a pretty unusual question. So normally, I'm personally more interested in the graph theory or in like those areas. So and I read somewhere that the logic is applied and in those areas or it works. So I am still having trouble how to think how to think about logic while doing those subjects, those topics.
Okay, so I will tell you one thing. You see, graph theorists have a concept that all graphs are finite.
Yeah.
Okay? In that case, logical has a minimal, if at all any, it has a minimal use. But there can be infinite graphs. Okay, they also crop up. Okay, and when you try to extend some of the results to infinite graphs, then logic is very helpful. And I'm giving you an example. Okay, about a result in graph theory which uses logic, and in fact which uses compactness theorem for propositional calculus, propositional logic, that Amit is going to cover next. Now, the statement is the following. Let G be an infinite graph such that F and K is a positive integer such that every finite subgraph is K colorable. Okay, you understand K colorable?
Yes, sir.
Finite graph K colorable, no two adjacent vertices will get same color and you use at most K colors. Okay? Then the whole of the graph is K colorable. Now, I don't know whether you will consider it to be a theorem in graph theory, because I know graph theorists who will run away if I go, and in fact, I had that experience. that I had a problem on infinite graphs, and I went to a guy, and moment he saw infinite graph, he said, no, I don't know. I said, look, this question is very simple. Listen to me, listen. No, refuse to listen. So then I cannot help it. But here is a statement that I have made. I can give many very natural examples of infinite graphs. Okay? And I have made, where did you go? Who was you? Whom I was addressing? So whom I was addressing, and can he unmute himself? What happened? Did he run away by hearing of infinite graph?
I think he got disconnected.
Oh, he is disconnected. Oh, I'm sorry. So anyway, all of you can think. I mean, a graph is nothing but a non-empty set of vertices V together with a set E of unordered pairs X, Y, X not equal to Y. So if this unordered pair XY occurs in E, you mean that X and Y are joined by a H. And K colorability I said. And now if I make a statement that every finite subgraph is K colorable. Okay. From there, I want to say, then for whole of the graph with infinitely many vertices, you will need only K color. So in graph theory, yes.
This is one of the examples I'm going to cover today. Yeah.
It is also in my book. It is also in my book. It is a direct consequence of compactness theorem of propositional logic. Okay. You have come now. You can take the stage now, Amit.
Yeah. I never left. I was always here.
No, you can take the stage now. There is a difference. I'm not saying that.
Yeah. I will.
Okay. So
let the host announce that.
Ah.
And yeah, some people might be having tea or coffee, so I will wait for that.
Yeah.
Thank you so much, sir, for this wonderful session. So it's almost time, so we can maybe start.
Shall we wait for a couple of minutes?
No, you can keep on chatting like I was chatting.
Yeah. I mean, the students will start that, but I won't start the formal
you won't
section.
start. I also didn't start my lecture before 2:50. Yes.
Sure, sir. So now I am I can hand over this to you.
Thank you.
Thank you, sir.
Yeah, participants, if you have any questions.
Sir, I have a doubt in the tutorial sheet, problem sheet, which
yeah, so I mean, we are going to discuss that anyway. If you have anything about the lectures, then let me know now. Okay, so yeah, I got an email. Yeah, I want to talk something about that, and I'm quite happy to discuss that issue. So, so here we are all studying logic and set theory. So one common misconception of participants, of students at their young age is that what is the real notion of a function? Yeah, can anybody unmute themselves and tell me what is the definition of a function?
There is a domain, and there are basically two sets.
Uh-huh.
and the set is defined from a set A to B,
Mm-hmm.
and all the elements of set A are mapped to set B.
Yeah. So
And
if I tell you that there is a function from Q to Q, which is the
yes, sir.
identity function, and if I am given another function which is the inclusion of rationals into reals, so are these two functions the same or different?
So can you repeat the function?
So there are two different functions. One is the identity function on rationals, and the second one is the inclusion of rationals into reals.
So what's the second function? Inclusion of rational into reals. Identity I got.
Yeah, inclusion means every
Then
rational number goes to itself. So that is what I'm asking. For you, are these two functions the same or different?
Sir, I think that if you consider the domain and one-to-oneness, then they are same. But if you consider the bijective property, then they can be different.
I'm not at all talking about properties of functions. I'm just
If you
asking
consider
you.
function as a triplet, the domain,
Yes,
codomain, then
correct.
not all of them would be same.
So a function is a triple. It is the domain, comma, codomain, comma, the rule that assigns to each element of the domain a unique element in the codomain. Okay, so this triple is a function. So the identity function on rationals is a triple q comma the identity rule, and so identity rule means what? It is a subset of A cross B, where A and B are the domain and the codomain respectively. Okay, so in the same sense, now we want to understand what is the meaning of a function from an empty set. From the empty set, yeah, there is only one, from the empty set to another set. So the domain is empty, the codomain is anything. Yeah, if you are interested in particular the codomain being empty, yeah, let us start with that. And finally, the graph, of this function. So we have to still explore whether there exists a graph, yeah, which will connect these two sets. So what is the property of a function that for every element of the domain, there exists a unique element of the codomain? Now this property is vacuously satisfied by this empty function, because there are no elements in the codomain, so we don't need to check anything.
yes, sir.
Yeah, so therefore we have a function with empty domain, empty codomain, and empty graph. Yeah, it is a function, and actually it is the function from empty set to empty set. And in fact, something more is true, that if A is any set, then there is a unique function from empty set to A. Yeah, it is the same function, the same graph. It is the empty graph.
Yes, sir. Yes, sir.
Okay. Anything else to say about this or other things? Yeah, see, my plan is to have a tutorial session split into two parts. First one, if at all there are any questions, I would like to discuss them, like apart from the tutorials sheet, or we can start with the sheet. So I know today I taught really fast. Yeah, after I went slow in the beginning to explain the idea of a language, a structure. Yeah, Nikesh.
Hello, sir. Sir, I have a doubt in one of the slides you presented in the morning. Can you open it so that I can?
Sure.
No, actually, there was one problem there. I think I have a doubt.
I will open that. In the predicate logic part.
Yes, sir. There was an axiom: there exists omega j such that you can insert it anywhere.
Yes, he's this one.
This one, F3.
Yes, F3. So what is the problem?
If you can do that for any formula, then why that? Where does that axiom help you? Like,
Okay, this is first of all not an axiom. It is a rule of constructing a new formula from an existing formula. Yeah, so phi x bar is a formula which does not mention the variable wj.
okay,
Yeah, we just have to ensure that there are no duplicates of variables. Yeah, that's why we are saying it is a formula that does not mention any wj. And whenever xi occurs, whenever the free variable xi occurs, we replace it with wj. That is our expression phi wj replacing xi.
okay, it's just like a dummy variable.
Yeah, it is a dummy variable. Yeah, and we are saying that we are replacing all occurrences of xi by a dummy variable wj, and we are not saying that this expression itself is a formula. We will instead put a quantifier, there exists wj, in front of that, and then say that this is a formula.
Okay, but then this depends on there exists the wj, right? If you don't put it, then it won't be a formula.
Yeah, see, the one thing that you should think about, that maybe the variable xi doesn't occur here.
Okay.
Yeah, xi may not occur at all. So I can say, okay, now I have replaced all the occurrences of xi by wj because there was no xi. And still I can write this formula. Yeah, there exists wj such that this is still a formula.
Okay. Okay.
Yeah.
Got it, sir. Understood.
Okay. Any other questions? Oops. I don't want to give you solutions directly. I will rather, yeah. Oh, wait, I need, just give me 1 minute. I will download the solutions, the tutorial sheet from my drive. Okay, yeah, here it is. Yes. So suppose L is a countable propositional language, then show that the set SL of all propositional formulas is also countable. So I definitely want to know the answers from you. This is a tutorial session, so we should discuss. Anybody is free to answer. And I hope these are not too difficult questions for you to answer.
So SL, we defined SL two ways. One was the inductive way. The other one was forming union of SNL where n runs over integers.
Correct.
Since L is countable, each of SNL would be countable.
Correct.
So countable union of countable sets would
Correct. Excellent. Excellent. Very good. So I have put this question only to connect it with the other course you are doing on cardinal arithmetic. Yeah, very simple idea, but very interesting question itself. And actually, as a continuation of that, yeah, so we have the second question. So suppose L is a countable propositional language, then show that the set of tautologies in SL is a recursive set. So all of you are learning about recursive sets, yeah, for past 3 days. So anybody wants to attempt this?
Recursive we defined as subsets of omega. So how are we going to?
Subsets of omega only.
Omega or omega to the power k. Right.
Okay, what is meaning of recursive set? Does there exist an algorithm which will terminate after finite number of steps and tell you whether that particular formula is a tautology or not?
Okay, yeah. So then here, if given a formula, it is going to be made up of finitely many
Variables, propositional
variables, yeah, and
variables,
then we can
correct?
just check all the possible to the power n values, and if
Correct.
for every
Very
value it
good.
gives a truth.
Correct. So the answer is via truth tables. Yes, very good. And actually, you can have an algorithm which enlists all the formulas in SL. Yes, this is the first one, this is the second one, third one, and so on. And you can do it for each one of them. And then you know eventually for each formula, you will have the solution for the decision problem. That this formula is a tautology or this formula is not a tautology. Yeah, so this is what, so propositional logic is easy in that sense. Yeah, that we can show that the set of tautologies is a recursive set, whereas the similar statement in predicate logic is not necessarily true.
But do we need countable here in the language? Because given a formula, it is anyway going to be made up of finitely many variables then.
I mean, I just wanted to be safe. I think algorithms are not talked about unless the language is countable anyway.
Okay.
I mean, how will you teach it? How will you teach a computer to handle real numbers?
No, point is even if I'm giving an input. So even if my input is coming from an uncountable set, my algorithm is going to
If
stop
your
into power
algorithm
n.
is, see, if your algorithm is depends on the input,
Yes.
yeah, then yes, it is a finite time algorithm. You can easily check it just based on the variables. But if your algorithm doesn't have any input, yeah, it just needs to produce the sequence of all tautologies and
Yeah,
not
it
tautologies.
cannot
Yeah,
produce, but yeah, it can surely check.
yeah. Verification is possible. Correct. Verification is possible without any assumptions on the cardinality of L. Whereas to generate the list, we need this assumption.
Okay.
Any so some of you are responding to my queries, but I also need to ensure that the rest of you are understanding. So if you have anything to ask or say, please do. Yeah, we are happy to discuss here. Okay, so in that case, let us go to question number 3. So show that this is a tautology actually. S implies negation, T implies negation, S implies T. And I'm asking you to write a proof of this. So if you don't mind, just get a piece of paper and a pen and start writing it. I will give you some time to think about it.
So we can use the truth tables directly, right?
How can you use truth tables? This is a single turnstile symbol. I'm not saying that use completeness theorem to show that, it is a tautology. I'm asking you to write down a formal proof. So I said lemma 4 can be used and deduction theorem can be used. So can anybody explain how I can use deduction theorem here? Like the first step?
Sir, if using
I'm
S comma not
guessing.
T,
Okay.
Yes, Dhruv, first step.
so like we can just throw in the S on the left hand side and then
Yes.
if we can show not T implies not of S implies T.
Very good, very good. S and negation. So second step, perhaps Ujjwal, you want to say?
I'm working it out.
Okay. So actually, once again, you have an implication on the right hand side.
I think I have it.
You have the entire solution?
Yeah, I think yes, sir. So
Okay,
we
can you
start with the set S, and
what is the set S here?
As in we're starting with the non-logical axiom with S as a non-logical axiom that way.
Okay, okay.
And
there is no set here. Yeah, the left hand side is empty.
I mean, yeah, I'm intending to apply deduction theorem later.
Okay, on what set? Like this capital S is empty in this case. This small s is a formula.
Mm. Sorry, no,
Okay,
no.
okay.
I had it wrong. I had it wrong. Sorry.
Okay, fine. Yeah, I mean, finally, if you get something like you can take both S and negation T on the left hand side, step by step, and then on this right you just have this. But this is an odd formula to work with. Yeah, negation S implies T is an odd formula to work with. But if you look at the particular structure of this formula, negation T implies negation of S implies T. And I will go to the notes of this. Yeah. Then, which logical axiom do you think will be useful?
The fourth one.
Which one?
The fourth one.
Fourth one, exactly. Fourth one could be useful. Okay, so T implies S. So let us look at that. Okay, sorry. I don't want to show the solutions as yet. So negation T implies negation S implies T should be this right hand side of this. So we need to talk about double negation somewhere. Yeah, we need to talk about double negations. So how to get that? So double negations are dealt with by using logical axiom 3. Yeah, so suppose we have double negation S implies T implies S implies T. Yeah, so something like that could be used. So that's why I was trying to reduce my screen and then show you step by step. Yeah, this is the first step. Double negation S implies T implies S implies T. This is LA3. And then you can use deduction theorem twice to take this part first on the left hand side and then S on the left hand side. Okay, what next? So I will try to walk you through the process.
Okay, so no, sorry.
Okay, so by using lemma 4, you can introduce double negation. That's why I said use lemma 4. So once you know T, then and you know lemma 4, you have T implies double negation T. And this lemma 4 doesn't have anything on the left hand side. But by monotonicity, you can put something on the left hand side. So we have this. Now the next step is obvious. Once you have T and you have T implies double negation T, you can use modus ponens to get double negation T. Right, now you have something here, double negation S implies T you have here, which you can transfer using deduction theorem to the right hand side, and you will get an implication of the form that we wanted earlier to apply LA4 at the end. Yeah, so see this. So you have transferred this double negation S implies T to the right hand side and you got this. And now use LA4. Yeah, simple. This implies with one less negation. This is LA4. And last step is that because you have this and you have this implies this, using modus ponens, you can conclude this. And you are done by using dt. So it is important to look at this, the sort, like the structure of the formulas to guess these proofs. Yeah. So it's commonly believed that there are some people who have the knack of getting these formal proofs very quickly, and others don't get it even after trying for hours. So this is a difficult thing to do in general, to come up with a proof of a tautology from just the given set of axioms. But our main point was never that. Yeah, we just wanted to make sure that there is a formal proof, or how it is defined, and there is a system, deductive system, deduction calculus, that makes completeness theorem true, soundness and completeness true. So this is an exercise which I just included so that you kind of try to think about it. During lectures, you just look at the axioms and go ahead. But here I wanted to take a pause and talk a little bit about this. Do you have anything to say? By the way, so earlier we had the bandwidth restrictions. Yeah, because of that, you couldn't switch on your cameras. I think with 59 participants, Zoom can easily handle all videos on as well. I mean, this is a tutorial session. It's meant for two-way interaction. If you wish to show your face, yeah, I would be happy.
Excuse me, sir.
Yes.
I had a small question here.
Yeah.
Like earlier when I tried to construct a proof by starting with a set of hypotheses, you said that deduction theorem couldn't be applied in that direction, as in we cannot like extract the hypothesis like from the set and bring it into an implication.
Because your set was arbitrary. You just used a notation capital S. That's why I said that.
Oh, okay.
If you had specified which set you are interested in, then yeah, definitely.
Actually, I was referring to small s.
Okay. Yeah. You could have said that, and yeah. Good. Yeah. Any other questions related to this? Fine. So let us say L is P comma Q, just two propositional variables in our language, and S denotes the formula P disjunction negation P implies Q. Can you find a formula T in the DNF, yeah, disjunctive normal form, such that S is logically equivalent to T using truth tables? So can you construct a truth table first?
P or P Q.
Sorry?
P or a bracket P and Q.
P or a bracket P and Q. Yeah, I mean, you should write these.
I think it will be not P and Q in the bracket.
Okay. P or?
P and Q.
P and Q. Okay. That is also a DNF, yes. But that is not the DNF in terms of atoms. Yeah, I mean, I'm asking you to construct it using truth tables so that you can do it for anything.
I didn't get. So DNF is
disjunctive normal form. Yes.
Yeah, of conjunction of literals.
Yes.
So here, so the literals are PQ, not P, not Q.
Yes. Correct.
So P or P and Q, I didn't get the remark which you said. You said something.
Yeah. So see, there is not just a unique formula in DNF.
Exactly. In fact, if you apply distributive, you get some other P and
yes.
P. Or,
yes.
yeah.
Yes. But I'm just trying to give you a canonical way of producing a DNF just by using truth tables.
Okay.
Okay, so there will be multiple answers, but okay, let us look at this. Yeah, this is the truth table I have written for you. Yeah, so this is how, so there were a few participants who had never looked at truth tables, and I'm sure they have run away by this time. This is end of third day. So let us have a look at this. So P, Q, P implies Q, and negation P implies Q. So we generally start with all the 2 to the n possibilities. Yeah, true, 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 false, false, true, false, false. Then P implies Q. This is the standard truth table. Yeah, true, false, true, true. And then you just compute this, and you observe that this is nothing but P. Actually, yeah, this second part gets absorbed in this. Okay, so true, true, false, false is what you get the column for this formula. Then you should read out the rows of the truth table. So P is true, Q is true. So you add P conjunction Q as one of the atoms. And for the second one, P is true, Q is false. So P is true, negation Q is true. So you add P conjunction negation Q as the other atom, and then the disjunction of these. This method will always work because your formula is finite, and finite formula will have only finitely many variables, and you will have all those rows which give you value true. You construct those rows into an atom if your language is finite. Yeah, of course. And then you get this.
So can you repeat what you said?
Yes, so whenever, like suppose this is my formula now. So I look at all the truths in this column. So I got T here. So I look at the corresponding row. So P is true and negation Q is true. So I will put P conjunction negation Q as one of the disjuncts. Yeah. So if I had also this one true, then I would put negation P conjunction negation Q, and then I will put a disjunction in between. The main advantage of reading this is that disjunction is true if and only if one of them is true. And atoms are defined in such a way that exactly one of them can be true at a time. Yeah, so we are in some sense writing it as a disjoint union of different parts. If you think about a Venn diagram, yeah, that's what is happening here. I'll soon show you a Venn diagram. Yeah? So yeah, are you okay with this?
This works because we're doing it in DNF, right? If we're doing it in CNF, we would have to do it differently.
CNF, yeah, you have to use the co-atoms. So atoms are the ones which are just above the bottom element. Co-atoms are the ones which are just below.
Yeah,
Below
the top element. Yeah.
top element, exactly. So that gives you CNF.
Okay.
Yeah. Okay. Then yeah. So one more thing I want to mention, that the finite proof that we obtained here, yeah, that is not necessarily unique. So Sujata has sent me a proof that is different from this, I think. I haven't read it completely, but yeah, you can have multiple proofs of the same tautology. So I just wanted to mention that. It's not necessary that you had to come up with the exact same thing. Right. So here is something else. Suppose L is 2-element set. Draw the Hasse diagram for the Boolean algebra SL/triple equal. Means the logical equivalence classes of propositional formulas. So can you, yeah?
Doubt. In fact, I had a doubt in this particular thing. So,
yeah.
Okay. So first we, okay, like just brute force, we need to first compute what SL is. So you start writing out P, Q, not P, not Q, P and Q. So in the first row. say, and then we want to compute the equivalence classes under the logical equivalence relation.
Yes.
So for that, first we need to find out all possible valuations on
Correct.
SL. So we proved a theorem. Once you define it on the basis, the elements on L, what the value of V is, it will extend uniquely to a valuation on SL.
Correct.
So ultimately, you will have only 4 valuations on SL, right? So which comes from true, 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 false, false, true, true, or P and Q respectively.
Correct.
So now once you've prepared this array of the SL elements on the first row and this truth values in the next rows, you need to search for identical columns.
Correct.
Yeah, so this is the algorithm, but then SL itself would be
SL would be countably infinite.
Yes.
Yeah, you don't actually go and search for SL. You are right. Like the algorithm is that you had to search for valuations, and those different valuations will form the atoms, and you just have to keep building from them. Just now I explained how to convert a row of a truth table into an atom, into an atom. Yeah. So just let me stop sharing this screen, and I have opened something in my browser. Yeah, I will. Yeah, I have opened something in my browser. So let us look at that. I didn't want to draw this picture. Yeah, it's already available on the internet. So let's use it. Yeah. So this is the falsity. Falsity is any contradiction. It could be P and negation P. Then this is P and Q. Yeah, I'm just reading it. Here it is written A and B. Okay, yeah, this is a better picture, definitely. A conjunction B. Then, yeah, this I think is NOR. Yeah, negation P and negation Q. From the picture you can see. This says P and negation Q. This is negation P and Q. Then you will have P and Q over here. Yeah, so don't get confused. Our propositional variables are themselves not the atoms. They will always lie in the middle layer because they are themselves constructed using all other atoms. Not all others, like some of other atoms. So these lines are what represent which formula implies which formula. Yeah, and you can check this picture in detail. Yeah, this is the top element here. These are the coatoms. Coatoms are nothing but the complements of this. So if you take this, yeah, take this atom, then you take conjunction of all the remaining ones. That will be one of the coatoms. Yeah, so what else we should say here, that every formula has a negation. Like if you look at anything which occurs at level 1, then its negation will happen at level 3. Anything which is in level 2 will have a negation in level 2 itself. Okay, so this is how we have these different things. These are the formulas. And you can compute the number of atoms and so on, given number of variables. And one interesting thing to note that because atoms are always finite so if you want to consider finite conjunctions of literals, so they will have finite length. But if your language happens to be infinite, then you will have no atom there, because every time you only choose finitely many variables. So P1 and negation P2 and blah, 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 something up to Pn. But you also have Pn plus 1. So you had to make a choice for that. And you can, in such a way, get a decreasing chain to the bottom. But that is a never-ending chain. Yeah, so those are atom-less Boolean algebras. Just for your information. Yeah, if your language happens to be infinite, then you encounter atomless Boolean algebras. Yeah. Any questions?
Sir,
again?
What is like the order here when we
Yes,
talk?
the order is, yeah. So order could be single turnstile symbol. It could be double turnstile symbol. It could just be that the lower formula implies upper formula is a tautology. Yeah, so all these things are equivalent. So the ordering in the simplest terms is given in terms of the columns of the truth table. So the target should have more true values than
Also subset, we can say.
Yes, exactly.
Okay.
Yeah, there is a lot that can be done, and like in a normal course we can do a lot with propositional logic itself. But of course this is a school where we have some specific goals in mind, so that's why I couldn't go into the details of that. But just to give you a glimpse of it, you can also study some interesting objects known as atomless Boolean algebras.
Okay, when it is infinite.
Yes. And atomless Boolean algebras are a good playing ground for learning about ultrafilters, because there are no principal ultrafilters there. Anyway, so yeah, so just look at this again. Did you complete?
So one more question.
Yeah, sure.
When we so it's like if we have n propositional variables, then there are 2 power n rows.
Correct.
So 2 power n would be the size of this.
2 power n would be the.
Sorry, 2 power n rows are there. So there are 2 power n possibilities.
Correct. Yes. So 2 to the power n will be the number of atoms.
Yeah,
and
but then how do I show that for every possibility there is a formula?
Because everything is a disjoint union of atoms. That is what this DNF theorem tried to do.
So that theorem is implying that. Yeah.
Yes. Yeah,
DNF. But then don't I have to also? Oh, so the theorem also has uniqueness inbuilt to it?
No. So unless you ask for atoms and your language is finite, there is no uniqueness.
No, for example, about the DNF form up to order.
No. So as you saw here, yeah, this column is exactly similar to the column of P. So
and both are
and P itself is in DNF.
Yeah, so but then isn't this an issue?
No, it's not an issue. There could be multiple formulas. The theorem about DNF only guarantees that there exists one, and if you look at the proof, it exactly talks about the truth table.
Yeah, okay, sir. Got it.
Okay. Right. Any other questions? Fine. So while we are on propositional logic and not talking about anything fancy, I just want to explain something about this adequate set of connectives. So what is a connective? Yeah, the formal definition has something different. I checked it on Wikipedia. We don't want to use any formal definition. Let's see that a connective, n-ary connective, is a rule of filling up the n plus first column of a truth table whose n columns and 2 to the n rows are already filled up. Yeah, for example, in this case, we have got 2 columns and 4 rows filled up by all distinct possibilities. Yeah, this is TT, TF, FT, FF. We have covered all possibilities. Then a connective is a way of constructing a new row. So that is a connective. That's all. So now let us look at this. So we say that a set of connectives is adequate if any propositional formula S is logically equivalent to a formula T that uses connectives only from that set. And I have given you a simple exercise to show that the Sheffer's stroke, as it is called, this NAND operator, is an adequate set of connectives. Yeah, NAND, all of you understand? It is negation of AND. Okay, so we had to show that this singleton is an adequate set of connectives, and what you should do, you should show that negation and conjunction, our two standard connectives with which we can obtain all the formulas, they themselves can be obtained using NAND. So do you want to try that? Yeah, should I give you a couple of minutes to do that?
Hello, sir. Is this similar to the universal gate thing?
Universal?
NAND gate thing in electronics.
Yes,
That NAND.
universal gate thing, correct. Yeah.
Okay.
Yeah, the person who has finished, please tell your answer. So first you should show negation can be obtained in terms of NAND.
So we have like if we take NAND of P and P,
correct?
That is like negation of P and P. We know P and P is P, I mean equivalent to P.
Correct.
So this is negation of P.
Correct.
And
very good.
Now, if we take, should I show conjunction or disjunction?
Conjunction, disjunction, any is fine. Either is fine.
It's like easier to show conjunction here, as NAND is just the negation of, I mean, NAND of P and Q is negation of P and Q. So we already know how to negate this thing. And
correct. Very
so
good. Very good. So I will just show the solution to everyone. Yeah, this last line is the solution. Negation is S NAND S, and S conjunction T is this. Yeah. Okay. So I don't want to spend any more time on that. Similarly, singleton NOR is also an adequate set of connectives. And there are some more things which you can do, but now that you're familiar with this concept, you can go and read more about it.
Hello,
okay.
Sir?
Yeah.
So adequate set of connectives, I mean, when we are taking NAND or NOR, let's say, so what are we considering? Like the and negation, or I mean, NAND as a whole? What is this set of
NAND
connectives?
as an operator.
NAND as an operator. And how is that a set of connectives?
It is singleton NAND. Yeah, I never said.
Right.
Yeah, it is singleton NAND. Yeah, yeah. So our normal adequate set of connectives is negation, comma, conjunction. It contains two connectives. One is unary, one is binary. Now NAND is a singleton binary connective, which is adequate by itself. Okay. Right. So once again, like a simple thing to do here, deduce completeness theorem version 1 from version 2. Yeah, these are versions, so they should of course be equivalent. And I will give you the proof in front of you of version 2 from version 1. Yeah, this is that proof. Yes, Ramakrishnan, you want to say something?
Yeah. This proof. So, so we need to deduce version 1 from version 2.
Correct.
So version 1, you start off with a consistent system, yes. No, a subset, yes, of SL, which is consistent.
Correct.
So claim is you need to produce a valuation which will model S.
Correct.
Now, according to version okay, so since S is consistent, you will have a T belonging to SL, such that S the T does not follow from S.
Correct.
That
Yeah,
not,
formally.
yeah, formally.
Correct.
Now, so you look at, am I allowed to use the contrapositive of?
Yes, of course. We have shown that contrapositives are same as the original statement. Yeah.
Then from the contrapositive of version 2, you will get that T is not a logical consequence of S.
Correct. Very good.
So from if I mean by T meaning a logical consequence of S, for every valuation of S which will model S, we'll have valuation of T to be true. So since this not being a logical consequence, you will get one valuation which will make the whole of S true,
but
T not true.
Correct. Very good. So in particular, V has a mod valuation
Yeah.
model. Correct. Very good. Very good. Yeah, exactly. That is the proof. Yeah, I hope everybody followed. He was talking really slowly, so that was very clear. Yeah, you start with consistent set, and then you just use the contrapositive of this theorem, and then you get what you need. Yeah, so that is a very simple thing to do. Okay, so now only one thing is remaining. I have literally given you the solution because otherwise I don't know how you will start thinking about this problem. So already SMS described a lot of things from this problem. Yeah, so a simple undirected graph is a set with a binary relation on it. And that binary relation has to be irreflexive and symmetric. So that is a condition to make it a graph. Irreflexive because we don't want to connect, we don't want to have loops. Yeah. And symmetric because it is undirected. Simple means no loops, no parallel edges, and undirected means symmetric. Okay, so this is k colorable, which means there exists a function f from v to set 1 to up to k such that what happens whenever two vertices are connected by an edge, x and y are in the edge set E, then fx and fy are distinct. That is the definition of a coloring of vertices. Yeah, there are also notions like edge coloring in graph theory. We are just considering vertex coloring here. Yeah, and the problem was already described that show that a simple undirected graph is k colorable if and only if each finite subgraph of G is k colorable. Now, one example of such a graph that you might want to think about is consider all pairs of real numbers which are exactly distance 1 apart. Yeah. Then consider all pairs of, like in real numbers, that we are considering R2. Yeah. We are considering the plane pairs of real numbers which are exactly distance 1 apart. And that is an interesting graph by itself. That is an interesting object of study. Yeah, you would like to know like what is this coloring number, for example. And yeah, of course, I'm not going to answer anything about that. Yeah, but this is just an interesting mathematical study where infinite graphs could play some role. Okay, so this simple undirected graph is k colorable. We want to show this, but this statement shouts for compactness. Once you look at it, it says that okay, something is satisfiable if and only if it is finitely satisfiable. And of course, this is not constructive. You cannot go on patching things and then finally get a coloring of the entire graph. That is not possible. So we need to resort to some non-constructive ways of argument. And we do that using compactness. That is the simplest way here. Okay, so the hint is that Pxi, yes?
So when do you say it is, when you say it is not possible, are there some results about that, or just because we're using axiom of choice?
We have to use axiom of choice in some or other form in this. Yeah, I mean, to show that we have to use it is difficult thing.
Yeah, that's what I was asking.
Yes.
Are there results like that also?
Yeah, I think that can be shown.
Oh.
Yeah, I mean, I'm not a set theorist. If there are set theorists listening to this, they can probably answer.
Okay.
So yes, let PXI. So we are going to describe a propositional language and construct a set of formulas whose satisfiability will be same as the existence of a coloring function. Okay, that's all we will do. That's our goal in this. So let Pxi denote a propositional variable for each x in V and a color I. And its intended meaning is that the vertex x gets color I. Okay, so let Sx denote this complex formula. What does it actually say? So let us look at the second part first. Can anybody say from the second part?
Every vertex has a color.
Every vertex has a color, yeah. Disjunction of Pxi for all i's. The vertex x has color amongst one of them. And the first part says that it cannot have two different colors. Pxi and Pxj is not possible. Okay, so it has a color and it cannot have two different colors. Well, that is the simple thing Sx says. Similarly, Txy says that for all pairs x and xy in V cross V, it says that vertex x and vertex y cannot have color I for any I. Okay, so they get distinct colors. Vertex x and vertex y get distinct colors. And then our capital S is nothing but this. So all the formulas Sx for x belonging to V and all the formulas Txy where xy's are the edges. Yeah, we are not going to do it for all V cross V. We are just going to do it for the edges. So we will ensure, so given this set S, yeah, given a model of this set S, we can construct a coloring function because that model itself will tell you, yeah, whenever Pxi is true, that is the color. Vertex X has color I. Yeah, so that is one thing. And whenever Txy is true, then two adjacent vertices in the graph get distinct colors. So we have constructed a function from the vertex set to 1 to up to k to the color set, which satisfies both these properties. In Sx, we have ensured it gets exactly one color, and exactly one color is enough. Similarly, conversely, given any coloring function, you can construct a valuation for this. How? Because that coloring function will tell you. So you will say that the valuation V assigns value true to Pxi if and only if f of x is equal to I. Vertex x gets color I. So this is just a straightforward verification of both the directions that satisfiability of S is nothing but existence of a coloring function. And then the rest is done by compactness. There is nothing remaining. Okay, so I have written something here. Yeah, you can check this. Yeah, verify that the function f is a coloring if and only if the valuation v defined like this is a model of S. You just need to check this and you are done. So very beautiful application of the compactness theorem. Right, so compactness theorem in propositional logic, even though useful, it is very weak. Yeah, it can only talk about connectives and we can have some simple results like this. So tomorrow we will look at compactness theorem in predicate logic, and that statement is strong. It has many useful consequences in mathematics. And in the next tutorial session, we will definitely have a look at least one application of that compactness theorem. But in any case, yeah, I mean, any questions about this? So I will also upload the solutions to the website. Okay, so there are 50 participants remaining. I'm going to take a poll right now. And the question, so you should tell me if I'm going fast or not. If you think I'm going really fast and I should say something more about other things, yeah, this is anonymous and everybody likes to answer anonymously. If I say something in the class, you won't say it. So if you think I'm going fast, please click on true. Otherwise, click on false. Okay, only half of you have answered so far. So actually taking a poll at random time also shows how many people are away from their computers. Okay, so only 21 people are listening right now.
That's a good one.
Okay, so I got answers from 23 of you and the results are 50-50. So I think I'm doing okay. Okay, Isha. Neither fast nor slow. Okay. Right. Yeah, I mean, I'm open to questions. Otherwise, we will have a session regarding student presentations. And those who are interested in giving presentations, I would request them to stay.
Hello.
Yes.
Yeah, I just want to one thing, like when do you say that your proof is constructive, and when do you say, like when you are giving a model and then you are saying that it is constructive, are you like the like we have used this canonical method and maximal consistent set, all these things?
Yes. So there is a formal definition of constructive mathematics. Yeah. You have to
Yeah.
avoid using certain proof methods. Like axiom of choice is one of them. You had to ignore that. Then you had to avoid law of excluded middle. I mean, just to give a brief idea about that to all participants. Yesterday, I said something like the moon is made of cheese, and it is not the case that the moon is made of cheese. Yeah. Similarly, you can say person X is good. What is its negation? The person X is not good or the person X is bad. Yeah. So in propositional logic, if you don't accept P, then you are forced to accept negation P.
Yeah.
Whereas in reality, we don't really want to accept that. Yeah. Negation P, that if the person is not good, that doesn't necessarily mean the person is bad. Yeah. So in that sense. Yeah? So that law of excluded middle is another thing that we want to avoid. And yeah, I mean, I'm not an expert on non-classical logics, but I think I can only think of that. Sujata, you might want to say something.
I think, is Ranjanda here?
Yes, I'm here.
Yes, okay.
Yeah, so Ranjanda, why don't you say something regarding this?
Okay, whatever I say will not be, I think, adequate for people who are trained so much in mathematics, because I do not come from mathematics. So, but then I am trying. The basic, it is related to some philosophical standpoint as well. I am from philosophy, so I know a little bit of background of this. So the basic idea is just this, especially for existence claims that something exists. Okay, so if we want to prove this, that there is an X such that X is P, this kind of a thing, then there are two ways in which we can prove that. One is we assume that it is not the case that there exists an x which is p. And then from that we deduce a contradiction. Because the contradiction is derivable from the negation of this existential claim, then we, by using this law of square and also the non-contradiction axiom of non-contradiction, then we say that then the claim that there exists an x which is p is established. But then this way of proving an existence theorem is not really also not really it doesn't really amount to produce an example of p which is there. So when we claim that something is p, we expect that we would also produce an example of that thing which is p, which we are claiming that it exists. So the other way is the other way of proving an existential claim is to somehow give a production of that particular object. So this is the main idea, that there is a direct proof for a sentence and there is an indirect way of proving the sentence. The indirect way typically uses this contradiction or reductio ad absurdum method, and the direct is that the way the sentence is constructed out of the connectives and or then quantifiers, etc., you go on giving proofs on the basis of those connectives that are used in the particular sentence itself that you want to prove. So that is the direct way of proving it. So whenever you go for direct way of proving, it is called constructive, because you are always giving an access how to convince yourself that yes, what I am claiming at this step is acceptable to me. Then the next step also, I'm convinced that this step is acceptable to me, etc., etc. This is what is called constructive proof. So this much I can tell right now. Okay, thank you.
Thanks a lot. Thank you.
Yeah, can I please add to something Ranjanda just said?
Yeah, sure.
Yeah. So Vinita, what you can think of from like interpretation, technical interpretation point of view, think of just the disjunction. You want to prove disjunction. A statement like P or some statement, phi or psi. So in the constructive way of proving it would be like you have to get a proof of phi or you have to get a proof of psi.
Yeah.
Okay. Otherwise you're not happy. So there is there is a kind of an interpretation of the proof there, and technically also the logic behind it is what we known as the intuitionistic logic. And one of the interpretations, the interpretation that we accept today for this intuitionistic logic is the Brewer Hating Kolmogorov interpretation, the BHK interpretation that you can think of, that we accept today. So you can look this up to have a more clear idea. Ranjana, of course, told the basic philosophical idea, and from the technical viewpoint, you can look at these interpretations. What are the properties there of those algebras? You can look it up.
Okay, ma'am. Yes, ma'am. Okay, thank you.
Yeah, just before we start, somebody wants to say.
Sir, I was like studying about like Buddhist logic in where it's a four-way logic of something is true, something is false, something is neither true, neither false, and something is true and false. So I found it particularly interesting. It's like can I find something somewhere in mathematics this Buddhist logic, something like this non-classical in mathematics? The four-way logic, not the just true and false.
So one suggestion I could give is that please look into Graham Priest's work.
Yes, ma'am.
Okay, please look into this work.
Yes, ma'am. Yes,
a lot of things.
Ma'am, what's the name? Graham?
Graham Priest. Grah. I can write it in the chat.
Yes, ma'am. Graham
Priest. The works of Graham Priest.
Yeah, I'll just say one thing. So I obviously don't want to ignore those who said that I'm teaching fast. Yeah, please read it this evening. Read through my notes and let me know tomorrow if you need any explanation. Yeah, we still have 2 more days to go. Yeah, I think we can end a live session now. And I mean the recording. recording, YouTube Live and recording. And those who want to give student presentations but cannot find partners or have some questions, please stay back.